we are recording. All right, so in the failed last recording, which nobody got to see, we were looking at the function f of x equals the natural log of the secant of x and taking its derivatives. Now, this one, actually, the derivatives aren't too bad for the first few, then they get a little wild, and so we whipped out the derivative calculator, right? And that reminds me, I need to give this guy some money. This is an awesome program. Natural log of the secant of x, and we want a whole bunch of derivatives. Just a quick recap here. Go. All right. Now, other things to note about the work here, we were centering this thing at 0, so we call that kind of Taylor series or Maclaurin series, so we'll see that terminology sometimes. And ultimately, what we wanted to do is generate a polynomial and use it to approximate the natural log of the secant at x equals negative 0.4. So we want to come up with a value for that. And to do so, I was going to use the 4th degree Taylor polynomial. So that means I need to calculate out 4 derivatives. If I want to test the error, I need a 5th derivative to do that. Any idea what the 5th coefficient is going to be? It's probably going to be a 0. If we look at it, we'll see that it's going to be a 0. And just a note on that, when you're testing error, it doesn't matter that the next coefficient is a 0 or not. If the 5th power is the next term, that's what you use in the error analysis, okay? And that always threw me when I first took this class years ago, that I thought, oh, I should use the 6th one because there is no 5th one. There is a 5th one, the coefficient is just 0, okay? But it still is involved in the error analysis, okay? So, and we'll do another example of that just to try and cement that fact. So in class yesterday, we looked at those derivatives and we determined that when we plugged in our center 0, we got the following function values for the derivatives. To generate the coefficients, we then have to divide by n factorial. Now keep in mind, it's always a good idea to make these tables when you're doing the Taylor polynomials as a reminder to yourself of all the steps to do. Sometimes when I don't write out the table, the derivatives are sufficiently complicated and I plug in the number and I spent so much time just coming up with these numbers, I forget to divide by n factorial. So it's a good idea to just write this out just to remind yourself to do it, because we'll look at another example in a minute that's a bit more complicated. And when I was doing it yesterday, I forgot to divide by n factorial and I couldn't figure out why aren't my answers working. So for our 4th degree polynomial based on the coefficients, we have this sucker right here. And we can easily just plug in negative 0.04 right now and get a number out of that, but we don't know how far off we are depending on the function. So what we next need to do is look at the error. So the error is the difference between the actual function value and what the Taylor polynomial says. Now, granted, we do know the actual function and we do have calculators that can use the natural log and the secant, but how does the calculator calculate the natural log of the secant of some number? Okay? They use some method kind of like this. Now, there are other techniques for approximations besides Taylor polynomials that you might look at if you get into some more serious hardcore math, but a Taylor polynomial up to a certain degree is an excellent approximation. So our next step is to say, okay, let's suppose we don't have the ability to calculate that. What's the error going to be? So Lagrange said that if you look at the next derivative in the interval of convergence between the center and whatever x value you're considering, there's always a magic number z that nails that infinite tail, okay? So it collapses down to a single term with the next power. This value of the derivative, now at the center, it may collapse to 0 for the coefficient, but it doesn't do that everywhere. There are other values in the interval for which that derivative is non-zero, right? So if we just take a look at that 5th derivative from the integral calculator, this function right here is non-zero for lots of things. It just happens to be 0 when x is 0. Otherwise, it is not 0. So it is a very relevant player in this game. And which one is that? Let's turn off some of these other ones. That's this guy right here, right? At 0, it's 0. Otherwise, it is very relevant. So we need to figure out how it's relevant. Now, we played with this in class the other day, and by looking at the graph, we determined that, oh, did we? Maybe we didn't. I didn't write anything down. Oh, we didn't get that far. Okay. Yeah, so that's the next step. So the next step is we need to look at this function right here and see if we can find a max in the interval that we're concerned about. And the interval we're concerned about is between the center and the value. Ooh, and I wrote those backwards. All right. So let's start to work. So that interval is backwards. It should be negative 0.4 up to 0. And there's a couple of options for doing that. One option would be to take the next derivative of this, set it equal to 0, and find any critical numbers, which would give us candidates for mins and maxes in that interval. Or we could just look at the graph. So, you know, 20-something years ago when I had to take this class, there wasn't a calculator that could graph this easily. So we had to take the next derivative and hope we could find a critical number in this region. If we didn't find a critical number in this region, what would we do next? Think back to Calc 1. In finding extreme values, you have two things you can do, or three really. You take the next derivative and you find anywhere it's 0, or anywhere it's undefined, or you check the endpoints. Okay, so if we found there weren't any critical values in that interval, then we would be looking at the endpoints, which is bigger, this number or that number when it's plugged in. So let's take a look at this in GeoGebra. And so I need what? This picture over here so I can recopy it. So we want to take a look at the function 8 times the secant raised to the second power x times the tangent raised to the third power of x, right now, plus 16 times the secant raised to the fourth x times the tangent, right? Okay, so that looks a lot like the graph that the integral calculator was showing us, and we need to take a look at that between x equals 0 and x equals negative 0.4, and then zoom in on this. I think we might have started this at the end of class, but I didn't write it down because this looks familiar. So one thing I like about GeoGebra as opposed to Desmos, it's way easier to rescale a graph in GeoGebra. So I tend to like it. Okay, so here I can see that there's an intersection point, and we better get more decimal places. Let's get 10 should be sufficient. We want to find that point of intersection. And GeoGebra says it's about negative 10.111196. So let's call it, and again, here we're concerned about absolute values of stuff. So we could call it 10.1120 to 4 decimal places. And my notes are back here. So we're coming up with a max, let's use red, of about 10.1112. And you always want to round up, never round down, because if you round down, you're less than that point. So even if it was appropriate to call it 10.1111, we wouldn't want to do that because that's less than the maximum. We have to be a little bit higher than the maximum. I thought I had 3 ones. No. 1, 1, 1, 3 ones. Let's blow up that font too so we can see it. Font size 20. Oh, I did put an extra 1 in there. You are correct. Good job. Yeah. So 1120 is what I meant to write. All right. All right, so now we have a candidate for the maximum value. So what we have now is we have again, our error is less than this, that is equal to this. Because we don't know the magic number z, we find a maximum of that derivative. We got the maximum, so now we have a calculation for what our error is. So now we just whip out a calculator and find out what that is. So back to, I'm going to ask GeoGebra. So I have a max of 10.112 times 0.4 raised to the 5th power divided by 5 factorial, which I think is 120. Get all the pieces there. Yep. Okay, and then I just plugged positive everything in there, so I got the absolute value covered. So this is telling me that my error is about 0.00086. 0.00086. So what that means is when I plug the 0.4 into my Taylor polynomial here, it looks like I have 3 decimal places of accuracy for that answer. And this is an overestimate of the error. We don't want to ever underestimate the error. That's bad, but that's an overestimate. So let's calculate the actual value next. So let's see, what was our polynomial again? Let's move you over here so I can copy you. Our polynomial is 1/2 x, x raised to the 2nd plus 1/12 x raised to the 4th. And I want to evaluate that at negative 0.4. And so I'm getting a value of 0.082. Too many different pointing devices here. All right, back there. So if I back up here, oops, that's not backing up. There it is. We have that the 4th Taylor polynomial evaluated at negative 0.4 is approximately 0.08, you remember? 82? And I'm not going to list more decimal places than that right now because according to our error, that's how many we know should be correct. Okay. Now, we have another benefit. We actually have a computer that can compute the natural log of the secant of x. So let's just kind of see what it looks like. See if we got that right. So natural log of the secant of negative 0.4. And 3 decimal places, 0.82. Yeah, so just like it said, we nailed 3 decimal places, but we are off on the 4th decimal place, was what it predicted. Now, we don't have the exact value we're off, we just know we're a little bit off there. So we tested this on a function that we know. The point of this is for functions that we don't know. So let's do a function that we don't know. So the function we are going to do next is, let's see, new page there. The following, we are going to consider, we're going to call it capital F of x, and capital F of x is equal to the integral from 0 to x of the sine of 7t squared dt. And ultimately what we want to do is we want to calculate f of 0.74, and we want to do so with a 7th degree polynomial. And then we want to estimate the error. Okay, so my claim is this is a function that we do not know. Why don't we know it? Well, if we try to take the integral of the sine of t squared dt, there is no 2t sitting out here for a substitution to fix for us, and integration by parts fails. Any integration technique we apply here fails. There is no fundamental antiderivative for this sucker. So the only way to calculate it is through some approximation method. Well, that would be a computer program. How do computer programs do it? Well, early in the days of computers, Taylor polynomials were the tool. You just had to go out far enough to get close enough to the number you want. Since then, people have developed other ways to approximate these things that are a little bit more efficient, but they're a little bit beyond the means of what we can do right now. So we're going to use the Taylor approximation. So to do something like this, I go back to what I know. Well, what I know is I know the sine has the following series. Remember, the sine is an odd function, so that means we're going to end up with odd powers of x. Odd powers of x would be x, and then it alternates sign. So minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And then dot, dot, dot. The general term looks like if we start counting with this as 0 and that as 1 and that as 2, then we're going to end up with a negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. So we derived that series last week using Taylor's method. And so next thing we need to do is we need to do a substitution in there. We're going to replace x with 7t squared and see what happens. So now we're going to make a new series for the sine of 7t squared. Oh, I forgot to mention an important fact here. We are centering this at 0. Okay. Otherwise, we have a little bit more work to do. And when you change the center, you can't, like if we made the center 1, you can't just substitute an x minus 1 everywhere, because in calculating the coefficients, you have to plug in the center to get there. Okay, so it's not just a shift. Although a function just shifts, Taylor polynomials do not shift. Okay, you have to recalculate all the coefficients, which is kind of a pain. And I think tomorrow we'll have a time to try that to see if a shift works, and we'll see that it doesn't. All right, so plugging in 7t squared for x, well, we get a 7t squared minus, if I cube 7t squared, I'm going to get what? 7 cubed t to the 6th over 3 factorial. And if I go to the next term, I'm going to get what? 7 to the 5th t to the 10th over 5 factorial. And if we wanted to, just for fun, we could get the general term, although we really don't need it because we only need a 7th degree. But if somebody said, hey, your error isn't good enough, we'd need to go out farther. So that would be negative 1 to the n. Then we would have a 7 to the 2n plus 1. Oh, I'm running out of room here. Let's have the magic pen fix that. Scoot you over. Thank you very much. And then we're going to have to then double 2n plus 1, which is going to be x to the 4n plus 2, all over 2n plus 1 factorial. It should be a t. Yes, thank you. We switched variables. Good job. All right, so if we needed to go up farther than 7th degree, we might want to know that. Now, just thinking about this, we're about to integrate this sucker right here, and when we integrate, we raise the power, which is kind of cool. That means I only need the first 2 terms, less work. I'm always happy with less work. Well, most of the time. All right, so next we're going to integrate this thing from 0 to x. And I'm just going to focus on my 7, so that means I'm only going to worry about the first 2 terms. I don't care about the rest, so I'm just going to go approximate now. And then the antiderivative for 7t squared would be what? 7/3 t cubed. And then I'm going to have a minus. I have a 7 cubed in the top, and the t to the 6th is going to rise up to a 7 and divide by 7. Right, so we're going to get a little cancellation there. So I think that's going to be a 7 squared t to the 7th over 3 factorial, which I'm going to write as a 6. And now I then have to evaluate that from 0 to x. And 0 works out very nice here, right? It just goes away. So now I can just rewrite this with x. And so my 7th Taylor polynomial for this particular crazy function is just 7/3 x cubed minus 49/6 x to the 7th. And I'm ready to do my approximation. So we're going to plug in our 0.74 into that and see what we get. So I'm going to whip out my GeoGebra is getting kind of messy here. Let's turn off a few things. Turn off, turn off, turn off. Okay, so new calculation. I'm going to enter my function 7/3 x raised to the 3rd minus 49/6, right? X to the 7th. All right, so that's what my 7th degree Taylor polynomial for that crazy integral looks like. And maybe I'll rescale to get a better picture of it. Oh, what happened? Oh, what? Where'd you go? Uh-oh, apparently I'm maxing GeoGebra out here again. All right, let's make this stuff go away. We don't really need it anymore. Oops. Isn't it fun when you do problems that max out your technology? I'm always impressed. It's happened to me. It happened to us in class the other day, didn't it? Right? What was it? I was trying to edit the series, and Georgia was like, "Sorry, not going to let you add any more terms. I've had enough." 49. I was doing a programming project like, I don't know, it's like 10, 15 years ago. And I was doing some really heavy computation, and the company I was renting the online computer from to do the computation called me. "What are you doing?" I was like, "Oh, I'm just calculating something." "Well, nobody else can do any work because you've taken over all the server processor. Can you please stop?" It's like, "Oh, fine. Please don't do it again without asking us." I knew they had a bigger computer than I did. So I thought, yeah, we'll do the calculation there. But they weren't happy with me. Apparently I wasn't paying them enough to do that. All right, so here's what our function looks like. Now the real function is a sine squared, and then we're integrating it, so it's probably oscillating forever, right? So we only have a little bit of it. The more terms we get, the more this would spread out and try and mimic that function. And so now I just want to know, what is f of 0.74? Is that what I said? Okay. And so we have that it is negative 0.04683. We don't know how many places those are correct, though, because we don't have a means to calculate that at the moment. So 0.0468. So let's write 4 decimal places down and see if that's correct. So f, or capital F, of 0.74 is approximately equal to t sub 7 of 0.74, and we are calculating that that is about 0.04, anybody remember? 68, thank you. 0.468. Okay, so next we want to try and find the error on that sucker there. So to analyze the error is always exactly equal to the next derivative. So that would be the 8th derivative of our function, evaluated at some magic number times our x value, 0.74 to the power 8, divided by 8 factorial. All right, so what we need to do is figure out how can we deal with that thing right there. And so let's go, oops, wrong direction. So now we need to figure out what to do about that number there. And this part's a wee bit complicated. What do I need to do this? Back here. So this is our function right now. When we take the first derivative of this, the fundamental theorem of calculus takes over, and the first derivative is just the sine of 7t squared. So we know that's the first derivative. So we need some derivatives after that. So I'm going to go ask the integral or the derivative calculator. And instead of entering the integral here, I'm just going to enter the first derivative. So for some reason I thought there was an easier way to do this, but I'm not thinking of it right now. And so that would be a 7x raised to the second. So that right there is our first derivative. Ooh, I guess I need to reload this page. Okay, so sine of 7x squared. And then we're going to go for some more derivatives. Let's go for 5 of them. Now, if I go to 5 here, which derivative really is that for me? That would be the 6th, because I already have the first derivative is what I'm starting with. All right. And then we can go ask, whoa, that's some crazy stuff. Whew. We're getting into crazy land now. All right, and then we're going to ask for some more derivatives, which I think I just clicked there. Is that right? Okay, so let's see. This right here was really our 6th derivative. So this is our 7th derivative here. And this one right here is our 8th derivative. Oh my gosh. Oh boy, look at that sucker right there. Okay, and then in our interval, that's crazy. Let's see, what can we do with that sucker? Let's copy that into our notebook. Oops, new page. Oh, what happened? All right, there you are. Oh, too big, slow down. All right, so let's see, what can we do with that? Thinking about a max for you. Max on 0 to 0.74. Oops, closed interval. Yeah, so this is a closed interval. So worst case scenario is we have our endpoint that we can use there. Yeah, wow, that's crazy. Okay, so we're going to cut our losses on this one and try a different problem. So again, sometimes these errors are pretty complicated. This one is, it'll take too much time to find the max, so let's do a more productive problem. How about, that's a good one. We just did one like that. All right, let's take a look at this one. Notebook. New page. All right, so we want to take a look at the natural log of 1.2. And we want to consider, let's see, for the natural log, let's center at 1, because the natural log is not defined at 0. And then we want to have an error of less than 1,000th. So to do this, we have to find ourselves the power series for the natural log of x centered at 1. So we're going to whip out our Taylor's method. And so we're going to have our n's, 0, 1, 2, 3, 4. And then we're going to have our function evaluated at our center, and then we take whatever number we get and we divide by n factorial. Does anybody remember off the top of their head the series for natural log? We've done this one a couple of ways before. Is it coming to mind? No? All right, let's see what happens then. All right, so natural log of 0 is, oh no, sorry, natural log of 1 is, we got to plug in our center of 1, 0, okay. And then we have to start taking some derivatives. And so the first derivative is 1 over x, or we could say x to the negative 1. And I guess I need another column here for that. And so when we plug in 1 to that, we get a 1. And then taking the derivative of that, we're going to get negative x to the negative 2. And when we plug in 1 to that, we get a negative 1. Next derivative would be negative times a negative, so that's 2x to the negative 3. Plugging in 1, we get a 2. Fourth derivative is 2 times 3, that's going to be negative x to the negative 4th. Plugging in 1, I get a negative 6. Let's do the fifth one and see if we see a pattern. What's that going to give me? Negative times a negative is a positive 2 times 3 times 4, x to the negative 5th. 2 times 3 times 4 is what? 24? Okay, so then we need to divide these guys by n factorial. So 0 divided by 0 factorial is 1. Or no, 0, sorry. 1 divided by 1 factorial is 1. Here I'm going to have a negative 1 divided by 2 factorial, negative 1/2. Here I'm going to have 2 divided by 3 factorial, which is going to be 1/3. And then I'm going to have a negative 6 divided by 4 factorial, which is negative 6 over 4 times 3 times 2, which is negative 1/4. Is a pattern evolving? Yeah, notice that these are basically factorials I'm generating as I take derivatives, but they alternate in sign, and they're one off, they're one less than the factorials I'm generating by n factorial. So essentially what I'm going to end up here is for any particular derivative, like the kth derivative down here, what I'm going to get is I'm going to get a k minus 1 factorial times x to the negative k. Right? Because notice 5 power, but 4 is the last factor of the product there. And then over here, I plug in my center, which is 1. So I'm going to always end up with a k minus 1 factorial divided by k factorial, which is always going to be 1 over k. And then I'm going to have a little multiplier of negative 1. And that's going to be to the power k plus 1. Or let's make it k minus 1 today. So the natural log has coefficients that come from the alternating harmonic series. All right, what's our center here? 1. Don't forget your center, right? Because often I'm stuck with 0 as my most favorite center. So what we've just established is the natural log of x centered at 1 is it's got no constant term. And then we have a positive 1 times x minus 1. And then we're going to have a minus 1/2 x minus 1 squared. And then a plus 1/3 x minus 1 cubed. General term is going to be 1 over n times x minus 1 to the nth. And then that should be a negative 1, sorry. And that's going to be to the power n minus 1. Because notice it's the even powers of the base that are negative. So we have to do a little shift there. And that goes on forever. All right, so next thing to consider, we are trying to calculate the natural log of 1.2. And we need to figure out how many terms we need to get the error within a certain amount. So we also want our error to be less than or equal to 0.001. Now our error is always going to be less than or equal to absolute value, some nth derivative, evaluated at some magic number, divided by n factorial, times x minus your center, right? Don't forget about that center, to the power n. Now, for us, for our error here, we can say that, let's see, what's an easy way to do this? Well, since we're picking x to be 1.2, then we can put ourselves in the interval from the center, 1, over to 1.2. So we're going to restrict ourselves to that interval in looking at derivatives. What's the nth derivative look like? Well, we have a formula for the nth derivative right here. I wrote it in terms of k. So we know that the nth derivative of z is going to be, let's see, what is it? N minus 1 factorial times x to the negative n. Is that the pattern we established here? Yep. So that's the derivative. So we could rewrite that as n minus 1 factorial over x to the n. Now, this is a decreasing function, right? It's going to be asymptotic at the origin. If it's a decreasing function, where does the max have to happen then on my interval? It has to happen at 1. Yeah, so that's kind of nice. So unlike that crazy sine function we were looking at earlier, it was really hard to figure out what it was doing, this one's actually pretty straightforward because it's a decreasing function. So we know that the max happens at 1. So for us, oops, because of these two facts and this thing right here, that we know the max has to be n minus 1 factorial. So coming up here into my formula, this thing with the magic number z is always less than or equal to the max. So now we have absolute value of our max, n minus 1 factorial, divided by n factorial. And our x value here is 1.2, let's see, yeah, 1.2. So I'm going to have my 1.2 as my magic x value. Notice x and z are not the same number. Notice I used two different variables there. Okay, z is a magic number, x is the number I'm interested in. So 1.2 minus 1 to the power n. And that sucker right there is what I need to keep under 0.01. So we just got to find a number for n to do that. Now, one thing that's super handy here, these guys clean up nice, don't they? Okay, so new page, 1.2 minus 1 is just going to be 0.2. So I have the following inequality. I have 0.2 to the power n divided by n. I need that to be less than or equal to 0.001. I have a slight problem here. I have n's both in the let's see, the base and the power. Is that going to be trouble here? I think it probably will be. 0.2 to the power n has to be less than or equal to 0.001 n. Yeah, we can't solve this for n because n is both in the exponent and not in the exponent at the same time. Natural log won't save us here. So the best we can do is then guess and check at powers of n until we are in the region we want to be. So spreadsheet's a good tool for that, or we could just guess with a calculator. You guys got calculators handy? All right, so 0.2 raised to the power, anybody give me a guess? 8, excellent. divided by 8 is 0.00. Yeah, that's plenty good enough. So 8 terms is way more than enough. Okay, let's knock it down a notch. Let's try 6 maybe. 6 gives me 1, 2, 3, 4 decimal places of accuracy. I only needed 2 decimal places of accuracy, so I can go less than 6. 4 maybe. 0, yeah, 4 works. 3 is probably not going to be good enough. Yeah, 3 is a little too big. We want it to be less than 0.001. That's 0.002. Yeah, so it looks like we need n to be 4 to get small enough. So this inequality isn't solvable. We can guess at n must be greater than or equal to 4 for this to work. So then from our polynomial, we can say that the natural log of 1.2 is going to be approximately, here's our guy right here. Now, remember, each time we take 1 away from it, so that means 0.2 is the number that's going to end up as being my base here. So I'm going to say it's going to be 0.2 minus 1/2 0.2 squared plus 1/3 0.2 cubed minus 1/4 0.2 to the 4th power. Should give me a reasonable approximation that's accurate to 2 decimal places. And again, we're taking it out to the nearest thousandth, but when I'm saying my error is going to lead to a 0 in 2 spots for sure, I'm a little bit off on the 3rd spot. Okay, this is an overestimate of my error, which means I might even be good to the 3rd spot. Okay, now that was a lot of work, right? Agreed? So was there an easier way to do this problem? Yes. What was it? Hint. Oop, hint. There we go. It's an alternating series. What's the alternating series remainder theorem say? It says look at the next coefficient. Yeah, just look at the next coefficient and that's your error. Okay, so that would have done it. So we didn't really have to do all this crazy work here because it was an alternating series. We could have used the alternating series remainder theorem. And one of your homework problems in 1011 says that. Hint, try the alternating series remainder theorem instead. It's way easier. So just a note, Taylor series remainder theorem is some big guns, but sometimes it's super hard to work with. We can do it, it's just computationally challenging. Anytime something alternates, you can resort to the alternating series remainder theorem, which says look at the next coefficient, that's as far as you need to go. Okay, so we are out of time for fun today, so I'm going to stop there. We will do more of this stuff tomorrow. There is a sample test. I'll post the answers to the sample test on Friday to give you guys a chance to play around. You should notice that 75% of the sample test looks just like that quiz I gave you, which I forgot to give back. I'll give that back tomorrow. So 3/4-ish of the test is going to be regular series and power series, no, regular series and, sorry, sequences, regular series, and then we have power and Taylor series. And Taylor series is just a class of power series. And I'll always break the test up into segments, trying to remind you, this part is about series, this part is about sequences, this part is about Taylor stuff. Stop.